Okay, folks, I'm gonna do a brief video here on a last reaction mechanism type that we'll discuss, and those are chain reaction mechanisms. And I'm just gonna do a couple of real examples to set that up. So this will be mostly qualitative. So the first example that I want to talk about is the ozone depletion mechanism catalyzed by chlorofluorocarbons by CFCs. And so many of you, I expect, are probably familiar with this, as it's a widely discussed phenomenon, right? This is the mechanism that led to the hole over the in the ozone layer. So here the CnFmCl, so that is a chlorofluorocarbon. And those things are very stable until they reach a certain altitude where you've got light that's super energetic. So that's smaller than around 300 nanometers or so. So that is energetic enough to pop off a chlorine radical. And that creates the initiation step in this chain mechanism. And now that chlorine radical can react with ozone that's present in the upper atmosphere in the ozone layer and make the hypochlorite radical and an O2. That hypochlorite radical can go on to react with available oxygen atoms that are present in the ozone layer naturally. And that produces another chlorine radical, which could then go on to react with methane and finally terminate. So what's important to note, this is a circular chain mechanism, and it's circular because the way in which chlorine is regenerated, it keeps this mechanism going round and round and round. Okay, and so the chain length, the number of times that this mechanism will go, is the rate of propagation divided by the rate of termination. And with this, one single chlorine radical, so one Cl radical, can destroy up to as many as 10 to the 6 ozone molecules. What's also important to note here is this isn't by any stretch of the imagination a complete mechanism. So for example, we talked about how ClO can react with itself to make the chlorine peroxide molecule. This hydrogen atom abstraction that chlorine does on methane isn't the only way that this mechanism could terminate as well. And notably, because this reaction is not fully terminated, right, we haven't shown also what happens with the CH3 radicals, right? Those are also gonna end up going through some chain reaction. This is a great example of a circular chain that will just keep going and going. So I'll contrast that with another example here. So this is a linear chain mechanism that will eventually terminate. And what's also important to note here, so this overall reaction is H2 plus Br2 to make 2HBr. So it looks like a very simple reaction, just hydrogen and bromine reacting to make HBr. However, it is a complicated linear chain reaction. So the reaction can be initiated by heat. And hopefully we can start to recognize that, right? When we see Br2 plus M to make 2 Brs, that's our Lindemann-Hinshelwood initiation. So where bromine would be the initiator. Or it could be initiated by light, okay? In either case, the reaction is initiated with the creation of bromine radicals. So this step with Br2 plus M is showing the heat initiation. The light initiation will also generate bromine radicals. And now those bromine radicals are energetic enough to split H2 into an H radical and HBr. Although with the bromine mechanism, The inhibition step, so that ends up being the K-2, that is quite substantial. That's very significant in this reaction. Significant. And it has to do with the HBr bond energy compared to the H2 bond energy. So a fair amount of this will actually move right back into bromine radicals. However, of course, we've still created H radicals, and those can also further react with more Br2s to make HBr. And then eventually this will terminate with Br and Br reforming Br2. So really that K1 and K4, that's the Lindemann-Hinchelwood. So that's the equilibrium between the initiation steps. Okay. So something entirely different happens if we look at H2 plus Cl2 to make 2HCl. Notice here the inhibition step is completely gone. And again, that's due to relative bond strengths of now HCl and HBr and H2. And we'll flesh that detail out in more detail in our live lecture. But it is important to note that when we change one player in a reaction, it might be the same type, like for example, replacing one halogen with a different halogen, but that can change the mechanism based on bond energetics and reaction rates. All the same, you can see with this reaction, in this case, it's being showed initiated with heat, but we could also initiate this reaction with light if we wanted to. And so similarly, we could see similar mechanism types if we looked at like the halogenation of an alkene. So that's a very similar reaction type. Or even the combination of organic radicals. That will also follow with this chain reaction mechanism where we have initiation, propagation, or inhibition, and then completed with termination. And so it's these reaction types that I suggest for your Kinetica project. These will make a fantastic example for your project. Okay, folks, I'll see you in the next video.